Hi, my name's Luca. I'm a fifth year PhD candidate in the Sageman Lab Group. I also work with Andy Matheson and Matt Herkin. Today, I'm going to talk a little bit about a current project on referring to sulfur system dynamics in a Holocene Scottish loch. This project is working closely with the Selby Lab Group in the UK across the pond at the University of Durham. So my main idea here with sulfur is like asking the question, how does changes in depositional system affect the isotopic composition of sulfides in sulfur as a whole? This is like a really old idea that actually dates back to the 80s. It was pioneered by Berner and Gautier and others. It kind of fell like by the wayside for a little while. The reason we care is sulfur is used, from a climate standpoint, sulfur is used widely as a paleobarometer. It's used to actually trace, make inferences on the rise of oxygen on our planet. This is done by comparing, in deep time, by comparing the isotopic offset between sulfates and sulfides. So when we look at our current paradigm, looking at this like global record of sulfur and using it to make wide scale conclusions on the redox state of Earth's surface might be a little more muddy than we think, given the possibility for local parameters controlling that signal. So really quick, the location is in far northwest Scotland. This is an isolation basin, and it was under the British and Irish ice sheets during the last glacial period. So during this, since the last 15,000 years, this loch has gone from marine to freshwater to marine to brackish and intertidal. And looking at the geochemistry of this record, it's actually kind of phenomenal how well these geochemical parameters kind of move with the change in depositional setting. What I'm mostly concerned with here today are the isotopic signals of sulfur. So, and when we look at that, this big change in the sulfur, both pyrite and bulk isotopic values, we do also notice that there's an offset, like between a few and up to like 12.5 per mil offset between the bulk and the pyrite records. This kind of really suggests that there are other sulfur phases in this record that are also pushing the bulk around. So this last summer, I went ahead and I did a sequential extraction of various sulfur phases that could also be influencing the bulk record. And I do not have the actual values yet. The EA is currently, she's getting ready. She's getting at it. But with a simple 2N mixing model for, say, if organic sulfur is also playing a role in this story, if we just keep a steady -5 per mil for organic sulfur, and base its influence on the TOC percentage for each sample. That way, we assume that the sulfur, the organic sulfur, is tied in with the TOC. We see that we can actually, come really close to replicating the blue, which is the bulk record, by adding that into the pyrite, right? So if we put those together, it really does. There is a way out of this offset, basically. And the reason we care, again, is constraining what actually controls the sulfur isotopic record and how depositional setting plays a role in that will lead to a much more honest use of sulfur isotopes as a paleoclimate proxy. With that. Questions? Anna?
So can you go back to do like
This one?
Yep.
That one?
This
That
one.
one? Yeah, so when I think when sea level rose, maybe that you see that increase in the Baltic profile. Overall, that sounds like, right in the between 16 and
Right. So maybe. So really, what's going on here? So let me. Okay. Yeah. Okay.
So I'm wondering if you have an explanation for why the whole study were at lower than the higher.
Right. Right. So on this question is if we all notice that everywhere else except for this freshwater pulse, you notice that the the sulfide, which is in orange, is actually more negative than the bulk signal, which is in blue. And that's generally what you expect because microbial sulfate reduction causes a negative fractionation. As astutely pointed out by Anna, this relationship flipped here. So I think obviously what it's showing is that there are changes to these other phases, right? In that's making up the bulk record. And here's one possible explanation. So obviously it's going to be a little more clear when I actually have isotopic values for these samples. But if we go through, we think about sulfate reduction here. Sulfate reduction, creating H2S, and here's the isotopic value bar. So we're getting more negative going down. So partial oxidation of H2S to elemental sulfur and creating pyrite there as a byproduct, right? If we go through this again, where this elemental sulfur that got created during this sulfate reduction gets reduced again to make more H2S. Now we have SO in the same stratigraphic interval as this pyrite that's actually more negative than the pyrite that preceded it. So it's basically this stepwise series of reduction and partial oxidation occurring at the same stratigraphic interval that might allow for an actual lighter pyrite signal than the bulk signal from the same sample. Again, this is something that would be, testable, hopefully, with actual isotopic analyses, but it is an idea. It's because it's a strange thing to ever see the pyrite signal be more positive than the bulk one. That makes sense.
Yeah, I guess like then that sulfate at the top of the sulfate.
Right.
Yeah.
Well, I mean, if we're looking at like in the pore spaces, eventually, especially in that freshwater lens, because we're in the freshwater when that switch happens, if sulfate levels become low enough, then we can start maybe seeing this like sort of, reservoir effect as well, right? Within the pore spaces where we're actually running out of sulfate. Not like the marine realm where it's a buffet. Cool.